Hi everyone, I am Sishun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I will talk about YOLO version 1, and YOLO is short for You Only Look Once. YOLO v1 is a unified real-time object detection algorithm based on convolutional neural networks and was published in CVPR 2016. The outline of this lecture includes introduction about the background and the idea of YOLO v1, unified detection, about the anchor mechanism used for object detection, network architecture for prediction, and the detection process. YOLO v1 training, about the way to encode the ground truth label, and the loss definition for training. Detecting objects in an image is an important topic in computer vision. So, what is object detection? Given an image I and a set of object classes to be detected, the object detection is to output the bounding buses of all detected objects and their object classes respectively. For the two object classes, person and ship, that are to be detected, the output of the object detection will be 4 bounding buses with their object classes respectively. In the object detection literature, most algorithms repurpose classifiers to perform object detection. A well-known algorithm in this category is FASTER RCNN, which is a two-stage object detector. In the first stage, FASTER RCNN computes the convolutional feature map of the input image, and then uses RPN, region proposal network, to output a set of object proposals. Object proposals are bounding buses that possibly contain objects. During the second stage, FASTER RCNN uses ROI pooling to crop the feature map inside the object proposal and normalize it into a fixed-sized and small one. After that, FASTER RCNN performs classification to determine the object class and regression to localize the object bounding box. However, there are two main drawbacks to repurpose classifier methods for object detection. Firstly, the detection architectures of this kind of method are generally multiple-stage pipelines. This makes the algorithm complex and slow. Secondly, each component in the pipeline must be trained separately, and this makes their architecture hard to optimize. Accordingly, the main idea of YOLO v1 is to reframe object detection as a single-stage regression problem. More specifically, YOLO v1 uses a single convolutional neural network to directly predict object classes as well as object bounding buses at the same time. This significantly simplifies the architecture and speeds up the detection process. The other idea of YOLO v1 is to encode contextual information. This reduces mistaking background pages as objects. More specifically, YOLO v1 uses features from the entire image instead of local pages for prediction. In other words, this convolutional feature map is used to predict the object classes and the bounding buses of all objects. For object detection, YOLO v1 uses the anchor mechanism as in FASTER RCNN. The anchors defined in YOLO v1 are S by S grid cells. They are obtained by firstly normalizing the input image to a 448 by 448 image, and then dividing the image into S by S grid cells. S is set as 7 in this work. In this way, there are 7 by 7 anchors, and each anchor is a 64 by 64 grid cell. The use of anchors is to encode the bounding buses of objects. The center point Sy is expressed as delta S, delta Y relative to the anchor that the center point falls into. The computation of delta S, delta Y is to subtract Sa, Ya from Sy, and then divided by the anchor size. Here, Sa, Ya is the coordinate of the left top point of the anchor. The width and height Wh of the bounding bus are encoded as delta W, delta H by dividing image size. This makes the Wh relative to the image size after normalization. Here, we take a green bounding bus as an example. The center point of this bounding bus falls into the blue anchor, whose left top point is at 192, 256. Accordingly, the computation for encoding the center point xy is shown in these two equations that are equal to 0.13, 0.87. For these two equations, they compute the box size relative to the entire image. That is 0.31, 0.56. In other words, using the anchor mechanism, this green bounding box is encoded as this one. Based on these 7 by 7 anchors, the YOLO v1 uses a convolution neural network to predict parameters for each anchor. These parameters are for 2 bounding buses and 20 conditional class probabilities. The predicted parameters for a bounding bus are delta S, delta Y, delta W, delta H, and C, where delta X, delta Y are the box center relative to an anchor. Delta W, delta H are the width and height relative to the whole image. Besides, YOLO v1 also predicts a parameter called the object confidence C to denote the possibility if whether the bus contains an object or not. For determined object class, YOLO v1 predicts a conditional class probabilities for each object class. Since YOLO v1 is designed to detect 20 object classes, it predicts 20 parameters, respectively for the 20 object classes. Accordingly, YOLO v1 predicts 30 parameters for each anchor. More specifically, for the defined 7 by 7 anchors, YOLO v1 is a single convolutional neural network that uses the entire image to directly predict a 7 by 7 by 30 feature map. Here shows the design idea of YOLO v1 network architecture. Inspired by the GoogleNet model, proposed in CVPR 2015. YOLO v1 uses 24 convolutional layers for feature iteration and 2 connected layers for parameter prediction. Similar to Lin's model proposed in 2013, YOLO v1 uses 1x1 kernels for feature reduction, followed by 3x3 convolutional layers. This table lists all convolutional layers in YOLO v1 network architecture for feature iteration. It totally has 24 layers. As mentioned, this network architecture uses 1x1 kernels for feature reduction, followed by 3x3 convolutional layers. For an input color image with 3 channels, passing through these 24 convolution layers outputs a 7x7 by 1024 feature map. The obtained feature map is then flattened to a 50,176 dimensional feature map. By passing through 2 fully connected layers, YOLO v1 outputs a 1470 dimensional feature map and finally reshaped it into a 7x7 by 30 feature map. Based on this predicted feature map, we then talk about the detection process to produce object classes and bounding buses. In the detection process, YOLO v1 generates B-bounding buses for every anchor. For each anchor with its corresponding predicted 30 parameters, YOLO v1 uses these 4 regression parameters to generate the first bounding bus according to these equations. These equations are simply derived from those for bounding bus encoding. Similarly, YOLO v1 generates the second bounding bus by using these 4 regression parameters. After that, YOLO v1 determines the object class L and the class confidence C hat of all bounding buses according to C1, C2, and 20 conditional class probabilities. In YOLO v1, the bounding buses from the same anchor share the same object class. The object class is the label that has the maximum conditional class probability. The class confidence C1 head and C2 head are respectively the object confidence C1 and C2 times P, where P is the maximum conditional class probability. By taking this anchor as an example, let the predictor parameters for the first box be 0.5, 0.5, 0.3, and 0.5. According to these equations, we can compute the center point and the box size of the first bounding box. Similarly, based on the predicted parameters for the second box, we can also compute its center point and the box size. For example, let C1, C2, and 20 conditional class probabilities be these values. Since P14 has the maximum value 0.8, the object class for these 2 buses is 14, denoting person object class. The class confidences are the object confidences C1, C2, respectively times 0.8, and result in 0.72 and 0.48. In this way, YOLO v1 totally predicts 98 object bounding passes associated with the object classes and the class confidences. After that, YOLO v1 processes different object classes separately via the following two steps to produce the detection results for each object class. Step 1 removes the passes with class confidences less than a defined threshold. Step 2 applies non-maximal suppression to obtain the final detection results. For example, assume that there are 4 predicted bounding passes for person and ship object classes respectively. During step 1, we remove this pass because its class confidence is less than 0.2. During step 2, we apply non-maximal suppression to obtain the detection results for person and ship respectively. Having detection results for different object classes, we then combine them into the final detection results. In this example, we detect 4 objects, 2 persons, and 2 ships. After introducing how to detect the objects by YOLO v1, we talk about how to train the YOLO v1 network. For a set of training images, we randomly select an image and encode its ground truth by using the defined anchors. At the same time, the selected image flows through the YOLO v1 network to predict a 7x7x30 feature map. Then, we compute the loss between the predicted parameters and the encoded ground truth labels. The computed loss is used to update the YOLO v1 network via backpropagation algorithm. Next, we will detail the way to encode the ground truth labels and to define the loss used for training. Label encoding is to use the ground truth labels, including bus center, bus size, and the object class to generate the encoded bus parameters and the conditional class probabilities for each anchor. Here, we use the symbol head to denote ground truth labels. The anchor that contains an object center is called the object anchor and is used to encode the object. Bounding bus parameters are encoded by the equations mentioned before, and the object confidence is set as 1.0. For object class arrowhead, it is encoded by using one-hot encoding that only sets the terms P sub arrowhead as 10 point. For the non-object anchor that contains no objects, all parameters that this anchor encodes are set to zeros. In this example, there are 4 objects whose center points fall into these 4 grids called the object anchors. The ground truth labels of these 4 objects are used to generate bus parameters and the class probability for all anchors. Since the first anchor is a non-object anchor, the parameters encoded by this anchor are zeros, and similarly for the second anchor. For the object anchor A11, we compute its bus parameter for the ship object. Set the object confidence as 1.0 and set the class probability term P head 16 as 1.0. We do the same thing until we visit all anchors. After introducing how to encode the ground truth labels by using anchors, we then define the total loss L used for training YOLO v1. L is defined as the sum of anchor losses Li over all anchors. To put more attention on the object anchors, YOLO v1 decreases the importance of non-object anchors. This is achieved by re-expressing L as the weighted sum of losses from object and non-object anchors, and setting the weight for non-object anchors as 0.5. These two terms are the indicators to denote whether these anchors are object anchor or not. In this example, we have 4 object anchors and 45 non-object anchors. In this equation, the term Li object is the loss defined on these 4 object anchors, and Li non-object is defined on these non-object anchors. The loss for object anchor is simply defined as the weighted sum of losses on 3 kinds of predictions, including box parameters, object confidence, and conditional class probabilities. To put more emphasis on box parameters, YOLO v1 increases the importance on the box loss by setting its weight lambda coordinate as 50. Then, we introduce the definition of these 3 losses. For the box loss, it is defined as the sum of squared errors on the predicted delta S, delta Y, delta W, and delta H of the responsible box. Here shows the definition of the box loss. These 4 terms are the encoding of the ground truth bounding box, and these 4 ones are for the predictions of the responsible box. The responsible box is the one of the predicted boxes that has the largest intersection of union with the ground truth box. For example, let this object anchor encode the ground truth object box as these 4 values. These 2 bounding boxes predicted for this anchor are shown as green and blue rectangles. Since the green rectangle has the maxima IOU with the ground truth box, it is called the responsible box and is used for computing the box loss. The box loss for this case can be expressed as this equation. As for confidence loss, it is defined as a squared error between the encoded and the predicted object confidences. For this anchor, its encoded object confidence is 1.0, and the predicted object confidence is 0.9. Accordingly, the confidence loss of this anchor is 0.9 minus 1.0 squared. As for class loss, it is defined as the sum of squared errors over all 20 conditional class probabilities, P1, P2 to P20. This equation shows the definition of class loss and can be expanded to this equation. According to one-hot encoding, this anchor encodes the person object by only setting P14 to 1.0. For the predicted conditional class probabilities as these values, the class loss can be computed as this equation. For non-object loss defined on non-object anchor, YOLO v1 only takes the predicted object confidences into consideration. It is defined as the sum of squared errors over predicted two object confidences. For this non-object anchor, let the predicted two object confidences are 0.5, 0.2. The non-object loss for this non-object anchor is computed as this equation and equals to 0.29. These two values are the ground truth object confidences for non-object anchor. In summary, the total loss is the weighted sum of losses defined on object anchors and non-object anchors. The object loss is the weighted sum of bus loss, confidence loss, and class loss. According to distributive property, the total loss can be expressed as this equation, where these three terms are respectively for bus loss, confidence loss, and class loss. By moving constant lambda coordinate outside the summation and expanding the bus loss, we can obtain this equation. Then, we expand the confidence loss and the class loss according to their definitions mentioned before. Finally, by expanding the non-object loss defined on object confidences over all predicted V buses, we have the form of the total loss definition for training YOLO v1 network. In this lecture, we introduce a single-stage CNN-based object detector called YOLO v1. Based on the defined anchors for object encoding, YOLO v1 achieves the object detection by using a single convolutional neural network to directly predict the bounding buses and object classes at the same time. The network used in YOLO v1 consists of 24 convolutional and 2 fully connected layers. For training, the ground truth labels are firstly encoded by using the anchors, and the total loss defined on object and non-object anchors is used for training YOLO v1 network. Thanks for your listening and have a nice day.